All right, so first of all, exam 1 is on Wednesday. That's 131, I think. And the topics are everything up through vectors, including vectors, yes. Not, but no kinematics using vectors. So in your notes, the stuff that's relevant goes right up until it starts talking about the position vector. Okay. When it defines the position vector, that the stuff after that is not on this test. Okay, so 7 and 8. Do you have the problems with you, or does anybody? And these are on vectors. Anybody have that? You had to derive the constant acceleration equations? Okay. Is that right?
Yeah.
Okay, so we're going to start with the acceleration vector as a function of time is equal to ax, ay, and those are constants, they're not functions. And we're going to derive the constant acceleration equations. And really the derivations go just like they do in 1D. So let's just break it up into x and y components. And, well, do we have to? It just takes more time, yeah. So, well, let's do it that way. Because I think it's a little clearer, too. Once this all like makes perfect sense to you, doing it as a vector isn't really difficult. But let's just do it all as scalar equations. So I'm going to start out by saying, so the x component of the acceleration is the derivative of the x component of the velocity with respect to time. And that's equal to this constant ax. And so if I integrate both sides, we get that Vx as a function of t is equal to the integral of this constant ax with respect to time. And so that's equal to axt plus some constant. And then we know that when t is equal to 0, the x component of the velocity is equal to v0x. That's a constant. And so we can plug that in and we get that the x component of the velocity is equal to axt plus v0x. And usually you see that just arranged the other way. It doesn't change anything. And then the y equation is the same. Any questions about that? Okay, and then from there, we know that this is the function for the x component of the velocity. And so we can say Vx of t is equal to dpx dt, because that's the definition of the velocity vector, and that's equal to v0x plus axt. And we can integrate that. So px is a function of time is equal to the integral of v0x plus axt integrated with respect to time. And so px as a function of time is equal to v0xt plus 1/2 ax t squared plus another constant. And now we know that time equals 0. The x component of position is equal to p0x. P0x is a constant. And so px t is equal to v0x times time plus 1/2 ax t squared plus p0x, and you can rearrange that to be p0x plus v0x times time plus 1/2 ax t squared. And you do it the exact same way to get the y component of the position. Yes. Yeah, sure. And then does this problem ask you to eliminate time and come up with an expression? Okay. So now we have these two expressions. And I'm just doing this with the x component again, but it works just the same with the y component. But we have that Vx, that's a function of time, is equal to V0x plus AXT. And we have that Px, that's a function of time, is equal to P0x plus V0xt plus 1/2 AXT squared. And so what I'm going to do is I'm going to use this one to come up with an expression for t in terms of v, v0x, and ax, and then I'm going to plug that into the second one. Yeah, you should be able to derive these. You should know these steps. All you really need to remember is that you start with the acceleration function equal to a constant, you know? Oh, yeah, you should be able to do that. All you do is take the simple one, isolate t, so come up with an expression for t in terms of the other stuff, and then plug it into the more complicated one. So if you rearrange this, you get that t is equal to quantity Vx minus V0x divided by Ax. Now plug that into the position function. And you get that Px is equal to P0x plus V0x times what we just got for time. plus 1/2 times ax times the square of what we just got for time. And now it's just, simplifying the algebra. Px is equal to P0x plus the quantity V0x Vx minus V0x squared over Ax plus if you square this, you get, I'm going to put the 1/2 in the numerator here, so I'm going to leave just Ax in the denominator. But you have Vx squared over 2 minus 2Vx V0x over 2, so that just comes out to be minus Vx V0x, and then plus V0x squared over 2. Now these have the same denominator. So you get Px is equal to P0x plus Vx squared over 2 these two cancel. And then minus V0x squared over 2. That's equal to Ax. And now that's over Ax. And now it's just a matter of, how you want it organized. Now I can rewrite this as P0x plus the quantity Vx squared minus V0x squared over 2Ax. And so then you can write it as 2Ax times the quantity Px minus P0x is equal to Vx squared minus V0x squared. Any questions about that one? Okay, and then what's number 8? Okay. Number 8 is the one where you eliminate t. Yep, so of those 3 expressions, this is the one if you don't know anything about time and you don't care about time, this one doesn't have time showing up explicitly at all. The other 2 both have time in it. Any other homework questions? Yes. The second to last one to the boxed one? Okay, so both of these 2 fractions have the same denominator. And so now I'm just adding up the terms. So V squared 0x. Yeah, okay, so you have V0x squared over 2 minus, 2V0x squared over 2. And so any other homework questions? Okay. So last time I introduced the 6 equations for 2D kinematics. Thanks. I guess before I do this, does anybody have any general questions related to the stuff that's going to be on the test? The stuff that we're going back to now is stuff that's not going to be on the test. So if you have any questions, I'd be happy to, you know. Yeah, in 1D? Okay, yes, let's do that. Let's do it. I'll give you a problem and you guys can work through it on the board, okay? So let's say a ball is rolled up a ramp with an initial speed of v0. It reaches the highest point on the ramp uh, 2 meters away. So first, what's the acceleration? And second, how long in time does it take for the ball to roll back to the starting point? Okay, yeah, good question. So I will give you, I'll give you all of those 3 main equations. So what you're going to use here is V is equal to V0 plus AT. P is equal to P0 plus V0T plus 1/2 AT squared. And 2A times the quantity P minus P0 is equal to V squared minus V0 squared. So get into groups and see if you can work through this on the board. So for this one, the first thing we want to calculate is the acceleration. We know that when it reaches the highest point, its velocity is going to be equal to 0. And so we can use the expression 2A times, I'm just going to write the equation first, quantity P minus P0 is equal to V squared minus V0 squared. we're going to call our starting position 0. When it reaches the top, speed is 0. And we know that at its highest point, it's made it 2 meters up the ramp, so that's 2. So we have 2a times 2 is equal to negative v0 squared. And so a is equal to negative v0 squared over 4. And then for part B, you could go 2 ways with this. For one thing, you know that the position is equal to 0 again. For the other thing, you know that the velocity, since it's back at that same location that it started with, anytime you have constant acceleration, the velocity when it reaches that same point is just going to be the opposite, same speed, opposite direction. So this is just going to be negative v0. And so either of those two approaches would work. With this one, you could say 0 is equal to 0 plus v0t plus 1/2 times negative v0 squared over 4 t squared. Solve for t. You can just factor out a t. Or you can use the fact that negative v0 is equal to positive v0 minus v0 squared over 4t. And either one of these give you that t is equal to v0 over 8. Yes. 8 over v0. That's what I meant. I thought I was solving for 1 over t. I wasn't. Any questions about that? You want to try to do a harder one? I don't know if I can think of a harder one on the spur of the moment. Okay, I'll try. Yeah. Okay. No, I will. Okay, so a ball is thrown up into the air, not just thrown up. From a height of 10 meters. It reaches a height of 15 meters. That's the highest point that it reaches. What's the elapsed time before it hits the ground? Yes. Highest point is 15 meters. Yeah. Okay. Let's see if you can get through that one. All right, so the starting height is 10. We know that when it reaches 15 meters, the velocity is 0. We don't know anything about the time, so we're going to use this equation. 2a times the quantity p minus p0 is equal to v squared minus v0 squared. This is 0 at the highest point. A is equal to negative g. Remember that if you use, I mean, you're welcome to just put the number in there, put in negative 9.8 or negative 9.81. But if you want to use g, remember that the variable g, the constant g is positive, so you have to apply your own negative to that. Well, it's just saying that gravity has a magnitude. What it's doing is it's not making any assumptions about your positive direction. Right. Like it knows it's down, but it doesn't know what you're calling positive. So right. Yep. So we have negative 2g times the quantity 15 minus 10, so 5, is equal to negative v0 squared. And we're doing all this just to figure out what v0 is, because once we have that, we can use one of the other equations to solve for t. So this says v0 is equal to the square root of 10g. And then once we have that, we can use the fact, we can use the equation P is equal to P0 plus V0t plus 1/2 AT squared. Now we're looking for the time when it hits the ground, so P is equal to 0. This is equal to 10. V0 is what we just solved for, minus 1/2 g t squared. Then you can use the quadratic formula to solve for that. I didn't plug it in and calculate numbers, but this is something like 0 is equal to 10 plus 9.9 t minus 4.905 t squared, and use the quadratic formula. What did you get for that? 2.76. Okay, 2.76. Oh, one thing about that, so the quadratic formula is going to give you two solutions. One of them makes physical sense in this case, the positive one. Mathematically, what is the other solution referring to? Do you have an idea of that? Yes, that's exactly right. So if you plot the position versus time graph, and here's 10 meters, and here's 15 meters, it's going to look like that, a parabola, sort of like that. But mathematically, there's also this stuff going on that never actually happened, and this is your second root. This is the one we want. Any questions? Okay, yes.
Would it have been possible to avoid the quadratic equation by plugging in the velocity, acceleration, position equation without time? Could you just plug in that for when t equals 0, and then use like the zero?
Oh, use that to solve for the velocity, and then plug. Yep, that'll work. That seems like a lot of effort to go through to avoid the quadratic formula, but yeah, you can do that. That's true, but you take the square root instead of, you don't have to solve a quadratic, right? You just take a square root. I guess I could see somebody theoretically doing that instead, yeah. Any other questions? Okay, so take a 10-minute break and let's come back at about 5:02, 3:02.